So today will be the second last class, but let me tell you what's going to happen quickly. Okay, the plan, specifically for section M. So for Wednesday this week, make sure you come. I will talk about the exam. Specifically, give you some tips about how you can get prepared. No recording, so make sure you show up. Okay. Also tell your friends who have been absent for a long time, ask them this is a class to show up. Okay. On Friday, I'll confirm with you the time. Friday this week, so that will be April 5th. We're going to have a makeup class. Well, but the reason is we're going to start a new topic about program verification. I'll definitely start with the topic today. I don't think really for me to finish properly, I can be done with that today and also Wednesday. I might need a little bit more time, a proper lecture to make sure I cover that. Okay, just a regular lecture since we're trying to make up a class. For next week, our exam will be Friday, April 12th. Somewhere between these 2 days, I'll choose one day to give maybe a review session. You basically study as much as you can, come to the review session, ask questions, and then we'll go from there. There's no agenda for this particular review lecture, completely driven by the questions you have. Anything you want to ask? Yes?
Okay, I know that EECS3311 is having a review at 2 o'clock.
Oh, say it again?
4101, that class is having a review at 2 o'clock on Friday.
Oh, 4101. Oh, sure. Can we, let me just make a record. Thanks. It's 2 p.m., right? Okay, 2 p.m. Friday, 4101. How many of you will be taking that class? But I can try to avoid if I can, right? Okay, 2 p.m. So any time between 2 p.m. will be okay, right? Okay, starting with 2 p.m. Okay. Yeah, I will take it into consideration, no problem. All right. For the plan for today, maybe in the very first 15 to 20 minutes, I would like to finish the event-driven design. And then after that, we'll start a new topic about program verification, which will last until this Friday. Okay, but for Wednesday, I would say, again, I'll talk about the exam tips on Wednesday only. Which one? You mean the makeup class? Oh, I'll give you the time. Because I tried to schedule that together with 1021. I'm still debating which time should go first. I'll let you know. I'll make a Moodle announcement, don't worry. Okay, Friday for sure. Hopefully sometime before 2 p.m. So we got a minimum clash. All right, let's now talk about very quickly about event-driven design. So the way for you to start study the observer lecture is to think about what the original problem is, and then think about how we have the initial design, the second design being the observer pattern, and then the event-driven design. Okay? Basically, if we want you to program on the paper in the exam, what should you do? Right? I'll highlight the critical parts you should know. Okay? Conceptually, you're thinking about for everything I'm trying to measure, I'm going to declare an event. Okay, we'll go over some slides quickly as we try to make a conclusion about this lecture about what event-driven design really is. In our case, you're going to have one event for the temperature, one event for the humidity, and one event for the pressure, right? For every event, for every measure you want to monitor. Okay, and then from each side, you may have as many subjects as you like. They can publish to these particular events when they have any change on the measurements. And also, subscribe to this particular event can be as many observers as you like, right? You got the many-to-many relationship, which can also be done by the observer pattern, but it's just much more complexity to keep track of. Okay, that's why we try to move to this more general design to support many-to-many. Any question about the general idea about event-driven? Good. So now we already went through the code in IFO. Let me just tell you again the important parts you want to focus. Okay, let's do very quickly. And for the Java code, I presume if you're interested, you can feel free to just have a look and play with it. You will not be tested anything about the Java code, but it's for your knowledge to really compare how you can do the same design in different languages. I think for you as a computer scientist, you really want to know the details. Okay, so now that's the Java side. I don't want to go in there. For the ISO side, let's go a little bit more different direction. The way I presented the code last time was going from bottom up, going from the way we did it was by saying we first have the events, and then we have the the subjects, the weather data, and then we have the observer, and eventually we get to the clients. Let's take the reverse order, just have a different way of understanding the stuff. Okay, I'll just go over them quickly and then highlight to you the stuff you should really pay attention to. So now, would it be too small for you to read, or should I enlarge that? I'll enlarge that, good, thank you. Let's start from the clients overall. You can think about weather station is really the clients of your event-driven design, okay? Let's think about what's gonna happen here. First of all, we're going to create this particular subject's WD, the weather data, okay? We're going to create this particular weather data, and as you do that, think about what's going to happen. So weather data is exactly over here. Okay, this is the subjects. For the subject over here, basically you have all your measures. You got temperature, you got humidity, also you got pressure. Okay, when you first initialize, you're going to make sure they all have the correct limits. Okay, again, one of the most important learning outcomes for you to learn from this course is to think about how to design contracts for your modules, for your classes. Okay? And then we also got the feature over here. You can have change on temperature, change on humidity, and also change on pressure. When we test you about your understanding about the event-driven design, number one, you want to know how many events you actually need in order to program your application. In this particular case, we got 3 different measures to observe. We got temperature, we got humidity, we got pressure. That's why I got 3 events. Okay? Each one of them is simply just going to declare of event type. And now you can think about this type over here is simply just about the arguments of the update feature. Okay, in this case, every update feature is just going to take a real number as the argument, as the input. Okay, we'll get there. And then there's simply just going to be a once, right? Remember the once we talked about in the singleton pattern, which means you're only going to create it once. You don't have to create a different events every time. Okay. Oh, there's something I didn't really highlight last time, but it should be once. Okay. Okay, so that's about what happened when you first create the subjects. So now let's talk about what happened when you try to create an observer. In this case, let's say it's a current conditions observer. Okay. So now for the observer over here, first of all, we try to say make the observer. Let's see exactly what's going to happen here. Basically, you want to make sure you build the link between the observer and the events, pretty much like this. According to the diagram, you want to make sure every observer over here, when it's first created, should be subscribed to the relevant events, depending on how many events they might rely on. Okay? So let me just take one example here. In the case of, sorry, that's a Java. In the case of the current conditions, let's go to the current conditions class. That's one of the observer. Let's see. You can see in the make feature over there, so given some particular subjects weather data, so now we know that the current condition is going to depend on the temperature and also the humidity. That is why we had to say change on temperature and change on, this one should be humidity. It's a typo. Okay, 2 different events. And then you simply try to subscribe to them. And what does it really mean to subscribe? Let's see what you have to pass as input when you subscribe. Rather than passing the whole objects, you want to pass just a pointer to the update feature for delay execution. As I said last time, if you have agent over here, it's a little bit similar to the star operator for referencing, right? If you want to get the address of certain function in C, you just say star, similar to that. Okay? That's how you can draw the analogy. So now when I first subscribe to this particular events, I'm just going to say whatever my update feature is for the temperature, I'm just going to pass a reference of that particular one. Okay? So now, of course, you should really understand if you get rid of the agents over here, it will not compile. If you simply get rid of the agent over here, that means to execute this feature right away without any delay. On the other hand, if you put the agent over here, you're saying that give this reference to somebody else. They can decide the timing of executing this feature. Okay? That's the most important part for you to understand for the observer. That's how you subscribe. Any question until now? We okay? Okay, good. Okay, after this, I'm going to do a little bit more. So now let's do the other part. We just talked about subscription, right? Think about we got events over here. Okay, you talk about subscribe from the observer. And also we talk about publish from the subjects. Okay, we just talked about this part, about the subscription. Let's talk about publication, or to notify, right? How do we do that? If you look at this point over here, let me use a different color. Let's say we try to say WD is a subject. And when we say set measurements, that means we're trying to change something. We want to change the temperature, change the humidity, and change the pressure, right? So what is it going to do? If you go to, let's switch the context to the weather data, which is a subject over here, okay? Let's have a look at the set measurements. Basically, what it's going to do is, in the case of the subscription, we simply store the pointer to the function for the updates. So now, in the case of publication, we're going to execute that particular pointer. Get a pointer there, and then execute the function. That's why delay execution. So the main purpose over here is simply just going to execute the store update function. Okay, the update procedure. So now you can see that over here, for set measurements, we're simply going to publish 3 times. Simply because in the case of, let me show the diagram again. So over here, we basically got 3 separate events. We got one event for the temperature, we got another one for humidity, and also we got another one for pressure. 3 of them. So you want to make sure whenever you make any changes to all the 3, you want to make sure you publish to all the 3 events. Okay, publish. Okay, so now if I go back to publish over here, let me show you one more detail. So what does publish really do? Okay, first of all, when you call the publish, we know that we're going to execute the delayed execution. We're going to execute that. So now temperature and humidity and pressure. So these. Oh, thank you. Thank you so much. Thank you. So now you can see all these published over here, right? So you can see tuple, and tuple over here. Okay, let's just tell you what these are. These are the input for executing the store update function. Because when we subscribed, we actually store the pointer to those functions. But now, in order to call those functions, we want to tell them exactly what you want to pass. And for all of them, you simply take one single parameter. Why only a single parameter? If you look at that, for example, in the case of current condition, you can see that their update feature over here only take one single input. So I want you to really draw a connection over here. This is how you declare, for example, update temperature, right? It takes only one single input. And then over here, when we try to publish, we just pass one single input in order to call that. Of course, if you've got 2 inputs, you pass 2 inputs. Okay, any questions? Yes? Yes, you may have more than one input. For example, okay, let me just hypothetically, let's do the following, okay? Let's say, for example, let me just say update temperature, right? Okay. Let's say for whatever reason, I just add another integer over here. Let's say I integer, just for the sake of a demonstration. So that means every time when I call the updates over here, I should really pass 2 inputs over here. So now when I get to change on temperature over here, when I say publish, so now rather than just a single one, I have to say maybe T separated by another I. Okay, because now it's expecting 2 input to be passed in order to do the execution. Which one? Oh no, only the temperature here only, because we only change the update temperature over here, right? Only that's to be affected. Right? You can, okay, again, what I'm trying to show you is if I somehow modify the header, the signature, for this particular feature by introducing an extra parameter. That means when you want to execute that feature, you should pass exactly 2 inputs. In that case, you might need something like this. That's why tuple is the most general way of passing the arguments, right? Yes?
You don't need to, I guess I understand your question.
Yeah.
Just have in event tuple square bracket.
Oh, yes, yes. I see what you mean. Now I see what you mean. Yes, you're right. Now I see your point. You're right. Also, we have to make sure this part over here is also changed to tuple, and then I got to say real, basically real, and also integer here. You're right. Yes, you're correct. Okay. Yeah, so everything just remain consistent. Okay, good. Okay, after this, we're just going to execute it, and that's how we do the things. Okay, one more detail to highlight. So now, if you go to the most basic level over here, which is events, okay? Basically, every time you want to create any events, this part over here, arguments, again, this argument is for the update feature, right? Update feature inputs, right? If it has only 1, you just pass 1. You have 2, like a real and integer, you pass 2 arguments. Okay, so this is just about a subscribe and publish. Don't memorize the code. We wouldn't ask you to write it. I think the most important part is to see from the subject and from the observer how you actually publish and how you subscribe. Okay, we'll definitely give you declaration for this. There's no point to memorize this, but understand what's going on here. Okay, any question about this before I just go through a little bit more slides with you? Okay, good. All right, so now let's do a final slides show quickly. Okay, so now let's go to event-driven design quickly. Okay, that's a diagram we talk about, and then let's talk about event-driven design. It's more like a summary, not that we have seen the stuff. In an event-driven design, basically now some terminology for you. Yes.
I do have one question.
Go ahead.
The idea is that weather data knows of the event, and events know of the actions that they need to be published in.
Mm-hmm.
The event doesn't know about the weather data.
Okay, let's see this. Let's go back here to the diagram. Okay, that'll be easier to illustrate. So think about what the events know about. For each events, they know about only the, you can think about abstractly, they only know about the delayed or the function, delay execution. They kind of know about what kind of delay execution I store in my events. They also know about, I also have a way to call those delay execution, right? So each observer, when first created, is going to store such delay execution in the events. Through the subscribe, yes. Every subject, when they got any change on the measurements, is going to publish. And by, when I say publish, he's going to publish by calling those delay execution. Yes. They don't, for the event, they don't have to know explicitly who the observers are and who the subjects are, per se. They just have to store the update features.
The feature that's being called within the object.
Correct. Right. It's just a feature that's going to be called. Yeah. We just don't want to dive into too much details. Yeah. Okay, that's good. Let's go back to the slides quickly. So now here's one word I would like you to be aware of. It's called monitor variable. The idea is very easy. You can think about any system you're trying to design. There's got to be a certain measurement you would like to observe. For example, temperature, humidity, and pressure. You can think about each one of them is going to be stored in the so-called monitor variable, which means they're being monitored by some sensors, right? You guys didn't really take a 1021. They do talk about how you go from physical sensors into software variable, but in your Android programming, similar. Whenever you do the button click, right, it's going to be somehow stored into some program variable as well. Okay, similar. So now, just to give you one example, let's say you got some nuclear power plant, right? The nuclear power plant got some very complicated chemical interaction going on. But let's say there are two things you want to monitor to make sure the temperature and the pressure don't really go too high. As soon as it goes too high, you want to do something about it. So it's event-driven. So which means temperature is going to correspond to one event, and pressure is also going to correspond to one event. Okay? They're going to be monitored separately, okay, by some observer. And then, so you've got two monitor variables for the temperature and pressure, and then, okay, you want to make sure as soon as things go too high, you can shut it down. Okay, just one example. Okay, so now, so we got observer should be subscribed to relevant events. It can be one or it can be more than one. And also the subjects, they can also publish to several events as well. Okay, the slide got quite many wordings over here, but I'm just trying to give you a big picture, right? Everything simply just corresponds to this particular picture here, depending on what your application is. Number one, you have to decide how many events you want to have. Number one. Number two, for each observer, each kind of observer, which event should they get subscribed to? And also number three, for each kind of subjects, when should they publish to each particular events? Okay, so three things. All right, so now if you go until the end of the slides, one more thing to point to you. Okay, everything has been said already. Okay, so now let me just go to the final slide to have a final conclusion. Okay, if you look at the final slides over here. Okay, so now basically we want to say that the event-driven design is doable in both iPhone and Java. Basically, you just have to translate each important concept into the corresponding programming syntax. So now in Java, you kind of need a hash table to actually map from object identity to the method handle, like a pointer to function. In the case of iPhone, you simply got a procedure. Okay, as I said, you don't have to memorize this, just be aware of that. And also, how do you actually create a pointer to function? In the case of Java, you have to look it up, right? Give the name of the method, give its context class, and also give the return type, and also a parameter type, right? All sorts of housekeeping stuff. On the other hand, in iPhone, you can just say agent over here. Okay, it just makes it easier for you to do such design. Okay. Okay, so now we just want to say it's easier to do event-driven design in iPhone because somehow they got a more convenient syntax for you. Okay. Okay, that's about for event-driven design. Any questions? Okay, exactly 20 minutes, roughly. Are we okay? Okay, as I said, you are not really expected to program everything from scratch. However, you are supposed to know the critical parts I talk about for observer and for the subjects. Okay, also the overall idea about event-driven design. Maybe study that. If you got questions, ask me in the review session next week. Okay, we're gonna have some review session for you. Okay, so now we're done with this one. So let's go to the final topic for the course. But this is gonna take today, Wednesday, and also Friday as well. Okay, let's take our time to learn about the stuff. I think the stuff will be very useful in the following sense. Friday, did you arrive late?
You were mentioning a makeup session, right?
Yeah, Friday. Yeah, I'll confirm the time later. That's a Friday. Yeah. Basically, this lecture over here is not really about programming, but in some ways trying to draw a connection between programming and also what you learned in 1019. Okay, we are basically trying the following. It's actually kind of beyond the scope of any languages you are trying to do. You might do in Java, you might do in iPhone, you might do in C. Every time when you have a critical part of your program done, you want to have some certain assurance whether that part of code is actually correct or not. And this lecture will be very useful, especially when your code involves complicated loops. You can really try to sketch your idea either formally or informally on the paper and do some proof, simple proofs. So it's quite a practical theory. Okay? So we're going to do, of course, the syntax we're going to use will be iPhone, but it can be translatable to Java or other languages. But let's start from the basics, and then we'll go step by step. Eventually, we are hoping that you can at least verify the correctness of a program that's that's at least complicated as like a binary search. Okay, that's something we are hoping with complicated loops. Let's start with some notational reminder. Okay, so we do talk about weak versus strong assertions. Actually, we talk about like a require less and ensure more. You know, back in the subcontracting lecture. Let's review very quickly. So now, for this particular lecture, we're going to use a weak versus strong. Weak simply means you got lower standard. When you have strong, it means you got higher standard. Okay, let's do one slide very quickly. So now you can describe each assertion or predicates as a set of satisfying value. Like you can draw a circle, right? Just like a diagram. For example, let's say you got two predicates over here. You got x larger than 3. You also got x larger than 4. Okay, so now we can right away decide which one is stronger, which one is weaker. Okay, let me just. Okay, so now over here you can think about x larger than 3 and x larger than 4. Okay. Oh, sorry. Let me just close this. Okay. So what I want to do is, okay, that'll be good. So now these two predicates here, okay, you can think about every predicate, you can just draw the corresponding set of satisfying values. In this case, it will be x larger than 3. So now if I want to draw the corresponding circle for larger than 4, should it be smaller, bigger, or the same? Smaller, good. Exactly over here. X larger than 4. It may not be to the scale. But now what would be inside? What would be outside this? Give me one value. 2? Are you sure? 2, really? 2 should not even be here, right? Good, 4. Okay, think about it. Basically, over here, you got 5, 6, 7, etc. Okay, over here, just include 4. That can be included, right? Are we okay with this? You're going to see lots of things like this you want to be able to do. Okay, so now, or mathematically, you would say x larger than 4 correspond to this particular set is actually a subset. And I'm pretty sure one of the theorems you learned back in 1019, implication correspond to the subset relation, right? Okay, implies over here, x larger than 3. If this is satisfied, this is also satisfied. And we say that this is so-called to be stronger. And this is said to be weaker. So when we say stronger versus weaker, it's relative. You always have some comparison. Okay? That could go absolute as well, having this in mind. Okay? So now, let's see this. I'm not too sure why you're seeing this. Okay, good. Okay, so now we got stronger, we also got weaker. Okay, so now, okay, again, you want to know the difference between stronger and weaker. When a predicate is stronger, that means it has higher expectation, which means it will allow fewer values, smaller set. Question for you. What would be the weakest assertion? Weakest. True, right? Weakest simply means what would be the predicates whose satisfying value is the biggest set? Cannot be any bigger. Basically, true is going to include every possible value, right? Always. Okay? What about strongest? Symmetric, right? False. False is the strongest assertion in the sense that it's so strong, the standard is so high, no values can satisfy it, ever. So the corresponding set is simply just empty. And I believe in 1019, what would be the set of satisfying value for true? What a set? It's called universal set, right? Huh? Yeah, just all the values. It's called a universal set. Okay? Yeah. Anyway, just some terminology reminder. So now let's talk about a little bit more context to our programming. Let's talk about design by contracts. Basically, every precondition, postcondition class invariants, you can use a Boolean predicates to specify them. So that's why we now want to say, whenever you're given a particular precondition, can we make it weaker or can we make it stronger? Similarly for postcondition and invariants. For example, we say that a weaker invariance has more acceptable object states. Well, what does that mean? Let's see one example. Let's say you have one bank account, one design for the bank account. Let's say version number 1, the balance is larger than 0, which means for the version 1 account to be valid, balance must be strictly larger than 0. Okay? Now, for version number 2, we say that balance should be strictly larger than 100. Okay? Now, we got two versions. Now, simple question to ask. Which class invariant is weaker? Greater than 0 or greater than 100? Greater than 0, right? Okay, very intuitively, you can see greater than 0, that means you can get 1, you can get 2, you get 3, all the way to 100. But these values are not going to satisfy the second version of the classic variant. Okay. Similarly, you can also talk about two preconditions and see which one is weaker. Whichever precondition is weaker, that means they are more tolerance. They can allow more values to be passed for the feature to execute, right? And also you can talk about the postcondition. If one postcondition is weaker than the other, that means they are more tolerant on the supplier. That means the supplier can produce more values than the stronger one. Okay. Okay, this slide just talked about weaker versus stronger, right? It's always relative. Any questions? Nothing new just yet. Nothing. Okay, I'm just trying to review a little bit. But I'm going to use these kind of concepts all the time. Okay. Okay, so now let's go a little bit further. Let's do a little bit discussion over here. If you look at this feature over here, just make it very easy. Let's say we got a class called foo. We got some attribute I. Let's say we got a feature, a command, increment by 9. And then we got some precondition here. We got some body of implementation. We got some postcondition. Now, by looking at this, do you think it looks right to you? Look appropriate to you? If you say no, can you tell me exactly why? How? Okay. Okay. Okay, sure. Yeah, I see what you mean. Let me recap exactly what you're saying. You basically, it might go wrong in the following sense. Let's say the input value is simply when I is, let's say it's simply just 4. When I is equal to 4, it's going to satisfy the precondition, which means we can go ahead and execute the body of the feature, in which case it's going to increment I by 9. In that case, I is going to be 13 afterwards. So now, having something that passed the precondition is going to give you something that's going to fail the postcondition. That's not good. Remember what we said before in the first lecture. If there's any contra-violation, either precondition, postcondition, or classic variant, there's something wrong. And what's wrong with this particular one is somehow you allowed, for example, this particular value over here being 4. And 4 over here is going to satisfy the precondition, no precondition violation, no warning. And then we allowed, so that's why we allowed the supplier's implementation to be executed. But after that, the resulting value over here is going to violate the postcondition. Okay? So now we say there's something wrong with this program over here. A very typical programming pattern goes like this, a very typical one. I'll give you some idea quickly. Let's say I got my feature over here, f, okay? You might want to think about what should my precondition be. Oops, spell it properly. Okay, so now I don't necessarily know what my precondition should be. I'll just put a question mark over here. And then I will simply say, at least I should really think about what should I achieve as a postcondition. So I might simply put some postcondition, let's say Q. Okay? I start with this, and then I give some implementation over here. And now after I have these two, it turns out there is a way, systematic, rigorous, and mathematical, to say, given the postcondition I want to satisfy, given the implementation I'm confident is going to work, we can calculate what should be the corresponding precondition I should put. That's what we're going to learn from this lecture. There's a way to calculate, but we're going to get there. Okay, that's just first example. So now let's see the second one. So the first example, the problem is somehow this precondition over here, tell me whether that's too weak or too strong. Too weak, right? Too weak in the sense that it's so weak, it also allows 4. That's going to be problematic. So we should really make it stronger. Okay, good. But we'll revisit this a little bit later. Let's see the second one. Okay, So that's exactly what you will see. Okay, it's too weak. And then let's see the second example. Let's have a look at this. Similar. First of all, can you tell me there's anything wrong in the sense of being wrong in the previous slides? Is the same error going to occur again? Are you sure? Thinking this way, if I'm given any I that satisfies the precondition I larger than 5, and I try to execute the body of the implementation as is, am I guaranteed to actually satisfy the postcondition? I am, right? Because the smallest value I can get will be 6. 6 plus 9 would be 15. 15 is guaranteed to be 13. Agree? Okay, let's make sure, first of all, it's appropriate. However, the second question would be, is there any scope of improvement? Okay, for example, you can see, first of all, if I got I, which is simply just 6, that's the smallest value you can get. And then I can say 6 plus 9 would be 15. And 15 larger than 13 is good. So it seems like there's no way for you to actually have a postcondition violation. Okay, first of all, it is appropriate in the following sense. Satisfying precondition and executing implementation guarantees the postcondition to be satisfied. It is appropriate in that sense. But now, let's talk the second question. Is the design too weak or too strong? Specifically for the precondition over here. Can we make it stronger though? For example, so now let's say this. If I make it stronger, in the following sense, if I make it stronger, let's say I larger than 4, would you agree? That's stronger, right? Would it still work? Oh yeah, sorry. It's a weaker. Yeah, yes, absolutely. That means you guys are awake. I like that. Okay, how about stronger? Let me say I larger than 6. Okay, would that be okay? Okay, make it even stronger. I larger than 7. It seems like anything stronger than 5 is going to be okay. All fine. Let's go the other direction. Let's try the weaker side. What would be the next weaker one? Okay, the one I got mistakenly written out. Would that be okay? Seems to be okay, right? Because the value would be, let's say 5, right? 5 plus 9 is going to be 14, which is larger than 13. Okay, so now this guy seems to be okay. What would be the next weaker one? Would that be okay? We just talk about it, right? So it seems to be some boundary over there. Some boundary. So this is the boundary we talk about. Let me just mention this verbally, or I can write it down as well. It seems like I larger than 4 is really the so-called weakest precondition for you to establish the postcondition. Anything weaker than that would not be acceptable. However, anything stronger than that would be okay. That's kind of the concept we are going to manipulate throughout the lecture. Okay, let me put it down. Okay, they are just motivating examples. We're going to see exactly how we can calculate systematically. So this I larger than 4 is so-called the weakest precondition to establish the postcondition. The postcondition. So now it's called WP. Okay, so now there are two things I'll just mention quickly. They may not make 100% sense right now, but when you review later after the whole lecture, it will make much sense. It's really the critical insight. There will be a way I will teach you exactly how you can calculate the weakest precondition. Once you get a weakest precondition, now you have a choice about how to design your actual precondition accordingly. Okay? A, precondition stronger than WP versus a precondition weaker than WP. Okay, one is about stronger, one is about weaker. Let's say I gave you the weakest precondition. So now you have to make some design decision. Should you make it a precondition actually stronger or weaker? Okay, so now here is a conclusion for you right away. Okay, stronger will be okay. However, weaker will be problematic. If your actual precondition is weaker than the weakest precondition, that means you allow some value that is going to have the post-condition violation. Okay, that's kind of illustrated in our two examples. But that's okay. I'm just trying to mention everything in one go in two examples. But we're going to revisit them. Questions? So say it again. I don't quite get you. Oh, why don't we simply get the strongest preconditions? You mean why do we use the weakest one rather? Oh, I see what you mean. Yes. I would say okay. Once you get a weakest precondition, okay, let's say in this case I can tell you the weakest precondition for this particular example would be I is strictly greater than 4. Okay, so now we say that I larger than 5, which is stronger, but it still works. I would say to really get something that's not exactly the weakest precondition is a design choice you have to make. Maybe for some reason, for your calculation, even though I greater than 4 will allow the most input values, but if for some reason you want to forbid I is being 5, maybe. It's a design choice. Nothing to do with the correctness. Okay? Yeah, we'll get there. Okay, so that's about it. But we're going to see lots of repetition later, just to really re-emphasize the points. Let me just tell you what you are expected to do later in the exam, so you have a clear expectation. In the exam, very likely you will be given a fragment of code involving possibly loops, selection, and assignments, or sequential composition. And then maybe with some post-condition as well. We want you to do, number 1, calculate what the weakest precondition is. Number 2, according to the weakest precondition calculation you obtain, now is your given code correct or not? Okay, so these are the two questions, but we'll go over them for sure. Okay, we'll go from the most basic level until the more advanced level. And for those of you who actually learned about 3101 or who are learning it, we're going to get to something to help you prove the correctness of loops, loop variance, and loop invariance. Okay, we're going to, in some way, it should really help you understand, because in the context of this course, your loop invariant and loop invariance, they are executable. So you really can see how things get executed at the runtime. Okay, we'll get there. Okay, so now let's talk a little bit about software correctness. Okay, and then we'll get to the WP calculation a little bit later. So now, first of all, understand that correctness is really a relative notation. What does that mean? When you were writing your Java code, let's say without any pre and post condition, in some way, it's really difficult to determine whether your software is correct or not. There's no specification. There's no design. But in the case of this course, we try to show you for every feature you're trying to define, put a precondition, put a postcondition, and put some invariance. Those constraints tell you exactly the boundary for what the correct feature should be. Okay? So now, it's a relative notation, so it should be the consistency between implementation and specification. And here, when we say specification, all the Boolean predicates for the pre, post, and invariance. Okay? Relative. So now there should be a specification. So for those of you, actually for your project submission, we are really looking for specification, right? If you only just give us code, that's not satisfactory. You need some contracts. Okay, so now this is the syntax you want to get used to. Okay, let me explain that. Eventually, we want to have a formal and systematic way to formulate your program and also its contracts. And then we want to understand the following notation over there. Okay, let's see how we can understand it. Let me just go to, let me just give you one example over there. Let me just copy this. Okay, so let's say we have our program over here. So this is what you're given. Okay, what's your task? Your task is prove or disprove, basically, that increments by 9, this particular feature is correct. Okay, that's your task. Okay, that's what you're given, and that's your task. Okay, let me show you what you're supposed to do as a first step. We have some notation for you to follow. You have to, first of all, formulate the whole thing. You can think about this is a single program. You want to formulate it into, formulates into some predicates. Okay, I'll talk about this predicate in just a moment. Predicate is simply an expression which will give you either true or false. And you want to prove that this particular predicate is a tautology. Tautology in the sense that this predicate will always evaluate to be true. Okay? But now, the question is, how do we formulate it and how do we prove it? Right? There are two concerns over here. Let's learn about how do you formulate it first. How do we formulate this into predicates? Okay? This is how we do it. Let me tell you the syntax. Curly brackets, some placeholder over here, curly brackets. Okay? What you put over here will be whatever precondition you have. And whatever you put in the middle will be the implementation. And whatever you put over here will be the postcondition. You might have the immediately following questions. What about the invariance? Any response to this? What about invariance? Invariant is simply the postcondition for every feature. So you can think about this approach also handles that. You can imagine that if the invariance is also important for the proof, it will also be included as part of the postcondition. Okay? So now, the syntax is really easy to follow. So now, how do I fill it in? Let's say here, the preconditions here, I larger than 5. The postconditions here, I larger than 13. And what about the implementation here? That's simply this guy here, right? I is assigned to I plus 9. Okay, guys, make sense? Okay, so now the whole thing over here is so-called Hoare triple. Anybody knows who Hoare is? Tony Hoare. You actually use his work extensively in your second year. Do you know quicksort? I hope you know, right? Yeah, quicksort is designed by him. He's a very important figure in software engineering research. And quicksort is one of his contributions, and also Hoare triple about program verification. Okay, just for your information. Okay, Hoare triple. Basically, Hoare triple contains 3 parts: precondition, implementation, and postcondition. Whatever you put inside the curly brackets should be a Boolean expression. Okay? And now, this part of the implementation can be arbitrarily complicated. It can be a single assignment. It can be if then else. It can be loops. Eventually, that's what we want to get into. So now, Hoare triple over here is simply just a Boolean. Okay? Most importantly, you want to know it's a Boolean predicates. So given any program over here, of course, it doesn't have to be just iPhone. We're just showing you in iPhone. Okay? Given any Java program, you can also formulate it as Hoare triple and try to prove the correctness. So that's why I said, whatever we give to you in this particular lecture is transferable to any other language, even Python. Right? Given any programming text, you want to formulate it into Hoare triple, which is Boolean. And how do you interpret the Hoare triple? Let's see the slides. Okay? Let's see that. Okay, there's a general form. You got Q, the precondition, R, the postcondition, S, the implementation. Okay, for example, you can see there's one example over here. Okay, of course, the pre and postcondition itself can contain conjunction, disjunction, for all, and exist, right? Everything you learned in 1019 is possible in your exam. Okay, everything. Well, hopefully not that difficult, but we'll give you an example to study, right? Okay, there's another one. And, okay, so now here's the thing. Before I talk about exactly what a Hoare triple really means, let's think about it conceptually. Once I formulate, let's say this, once I formulate program version number 1 where the precondition is simply I larger than 3, and version number 2, I is larger than 5. I got 2 Hoare triples, right? If I want to prove each one of them is correct, I have to prove that the predicate is a tautology, always true, right? So now here's the principle. If the Hoare triple you formulated can be proved as true, always you can say the original program is correct with respect to its precondition and postcondition, the specification. For example, I'll get to there later. In this particular one, remember we talked about this example here. We say that even though I larger than 5 can be made a little bit stronger, but that's okay. We only worry about whether that's correct or not. This particular Hoare triple here, eventually we'll see it can be proved as true, eventually. Okay? On the other hand, if the Hoare triple you formulated cannot be proved as true, which means you can find some counter example. Let's say this guy here. If I got I larger than 3, right? In this case, one counter example could be, what if I is equal to 4? If I is equal to 4, 4 larger than 3 is going to be true. So we go ahead and execute the body of the implementation. 4 plus 9 will be 13. But 13 strictly larger than 13 would be false. So that would be a counter example. So eventually, you will just have to do lots of formulation of your progress into Hoare triple and then try to prove it. And we do have a template for you to follow, how to prove it. It's quite intuitive if you understand things step by step. Guys, any questions up to now? Yes? Say it again, I don't quite catch that. Yes. Yeah, basically think it this way. Think it this way. So now, let's say this. I is assigned to I plus 9. I larger than 13. Okay, let me give you the 3 different versions. 1, 2, and 3. So now version number 1, I larger than 4. I larger than 5. I larger than 3. So we got basically 3 different versions of the formulation because they come from different versions of the program. Okay, let me just tell you, we'll see exactly how you prove. It turns out these 2 are tautology, which means somehow we can prove that it is true. Okay, but this one here, we can disprove by saying counter example. Let's say I is simply equal to 4. But we got to see exactly how we prove it. We'll get there. Guys, are we okay with this? Okay? Yeah, we're just trying to go step by step, right? Otherwise, we'll throw too many details to you. One go, that'll be too overwhelming. Okay, so let's go a little bit further. Hoare logic. So now let's consider what the Hoare logic really means, a Hoare triple. Okay? Basically, again, let's remember this is a form. Okay, let me just write it down again before I show it to you. So we got precondition Q, and also we got postcondition R. Yes. Okay, that's the form we have. Implementation, precondition, postcondition, right? Now, how do we understand it? So this is so-called the correctness predicates or Hoare triple, either way. Okay. So when we mention about correctness predicates or Hoare triple, they mean the same thing. Given a program S and also its pre and post condition, you can formulate it right away by following the syntax. The formulation part is really easy. Just copy and paste. That's it. It's really about the proving that's going to be more complicated. Okay, so now let's see how we can understand informally what it means for a Hoare triple to be a tautology. Okay. So given pre and post condition Q and R and also implementation S, it would be a tautology if program S, the implementation, they will start executing in a state that satisfies the precondition Q. And then it's going to execute the implementation there and then terminates. So termination here is really important. Well, if you only got, let's say, if statements and also assignments, termination is not really a concern. It's only when you actually got the loops you're going to worry about termination. But to be realistic, you always got loops in your program anyway. Okay? So now let's talk about it. So now first of all, the program will terminate. And also, you want to say that if the program terminates, you want to make sure upon the termination, it's going to establish the post condition. So we got two concerns over here. Two. Concern number A is only about whether or not the program is going to terminate. Okay? And concern number two, assuming that your program is going to terminate, is it going to establish the post condition at the end? Okay, so these are the two concerns. Okay, so now we got these two, termination and also B. So now just a little bit more terminology. You can see for concern number B, okay, for B over here, we simply say we don't really prove any termination in B. We assume that's the case. In that case, whatever we can prove for B is so-called partial correctness. Okay? Let me just illustrate to you quickly. So now if I got Q over here, R over here, and S over here. So now we got A is simply to say, starting with Q, that's a precondition satisfied, and executing. Oh, sorry, I got that wrong. That should be S, that should be R. And executing S will terminates. So A is about termination itself. What about B? B is to say, let's not worry about termination for now. Okay, just assume that's the case, so we can have separate proofs. Assume A. Does the resulting states satisfy the post condition R? Okay, so now you can see that over here we simply assume termination is the case. It may or may not be the case. Okay, so now if you can prove B, it's so-called partial correctness. In the sense that if you only try to prove B, you are not really proving termination. You just assume that's the case. And now if you combine A and B together, it's called total correctness. So think about partial correctness is total correctness minus termination. Okay? Some terminology here. Any questions about this? We haven't got into how you calculate WP just yet, but we'll get there. Not yet. Okay, that's about, okay, you can see A plus B together will be total correctness, but only B alone is called partial correctness. You got to combine with a termination proof. Okay, so now let's do a little bit more illustration over here. let's say we do have a Hoare triple over here. Let's say we got precondition, postcondition, and also implementation. Let's think about the different combinations of the Q and R. Okay. Okay, that's a notational convention over here. Let's say this. What does it really mean when we have this Hoare triple here? What does it really mean? Tell me something. This program here, what's the characteristic of this program here? If we can formulate such Hoare triple from the source program and this specification. Somebody? Huh? Basically, no precondition in the sense that any input value will be okay, right? So that means very easy for the client to use. Any input value will be okay, right? You will never have the precondition violation. All the input values are valid. Okay, it's very user-friendly in some case, right? Any input value will be okay. What about this? The opposite, right? So that means it'll be very useless to the clients. Any input value they try is going to fail anyway. Very useless. How about this? Let's say you are the supplier. Would you be happy to implement something like this? You're the supplier. Why? Why would that be easy for you to implement? Yeah, because in this case, the post condition is simply true. That means it doesn't matter what I do, you will always be satisfied. I can print out just hello world. I can simply do nothing. I can simply give you an infinite loop. It doesn't matter. You will always be satisfied. On the other hand, if I'm your boss, I say, if you can finish this by the end of the month, I'll give you a promotion. Would you be happy with it? This one? Really? Would you be happy with it? Does it really matter what you do for this program here? Well, it doesn't really matter, right? Because over here you can see the post condition here is simply false. It doesn't really do anything. Even if you give me a very efficient sorting algorithm that's even better than n log n, doesn't matter. Even that, you're going to just have false as a post condition. That status so high is empty set of satisfying value for false. Okay? I'm just trying to give you, different combinations of the pre and post condition to the extreme case, so you really get a feel about how we can design, the predicates for pre and post condition. So apparently, each extreme case is not advisable. You want to go somewhere in between. You want to tailor to your particular application. Okay, it's very challenging to coding. Okay, basically infeasible. Okay, what about this? Well, seems to be very user-friendly. Anything should be able to be passed. Also very easy to implement because anything is going to satisfy. Well, somehow you're lying to yourself, right? You simply got no precondition, no postcondition. It's as if you came just right before this course, right, for the Java. No pre and post conditions. Hopefully, you will never run into this situation after you graduate from this course. Hopefully, that's my hope. Otherwise, you got to retake it with me in the fall. Okay, either way. Okay, guys, any questions about this? Are we okay? Mm-hmm. Okay, basically no contracts. So that means it's very, very, very bad in giving information about how the modules should work together. Okay, so now we want to talk about weakest precondition. Okay, you know what? Let me just see exactly what I wanted to present. Okay, over here. So now let's talk about some conceptual idea, how things will work. Okay, so now what we want to do is, let's say you're given a Hoare triple. How exactly do you prove? What kind of proof procedure do you have to follow to prove that it's a tautology? Okay, so now let's see this. Let me just show you this right away. If you are given the Hoare triple like that, it will be true if and only if the right-hand side is true. Okay? Now let's see exactly what's going on. And then you should really get some intuition. I'll give some intuition verbally, and then let's draw some diagram as well. Okay? Let's say this. So you got your Q, precondition, implementation, and also R. This is the predicates. How do we prove? Basically, what we're going to do is, it will be true if and only if the following. First of all, you're going to learn how to really calculate the weakest precondition called WP. Okay? The weakest precondition is going to take two inputs. First of all, it's going to take the programming implementation, S, and also it's going to take whatever post-condition you want to establish, and WP itself is a predicates. WP basically tells you, given the implementation you have and given the post-condition you have, what should be the weakest precondition you must have. Anything weaker than that is not good. But anything stronger than that is good. It's okay. It's acceptable. So now, question for you. Assuming that WP, you know how to calculate already, let's say, you're given. What should be the relationship between the actual precondition? Yep, I'll get there. This is whatever precondition you chose to have, and this is the weakest precondition in theory. So now, what should be the relationship between these two? Should I say this implies Q? Why not? Really? Oh, not good. Not good. Feel free to write that in the exam. That'll be easier for me to mark, actually. Yeah, no, that's not good. Okay? Basically, you want to say, because this guy here is already the weakest, thinking this way intuitively, if that's theoretically the weakest, you cannot go weaker than that. Okay? So that means anything stronger than that will be okay. Q here, which means Q must be no weaker than the weakest precondition. Okay? Are we okay with this before I show you some diagram? Okay? So now this diagram really summarizes exactly what we're going to do. Okay? Let's see this. Let's say we got, let's say, the implementation here. And this is kind of the implementation. Okay? We're going to execute. And then we're going to say that at the end of the implementation, we would like to satisfy this post condition. So we can think about this is the post condition, which is going to be the set of values that's going to satisfy R. Okay? So we're given the blue, given the pink. Following some systematic procedure, conceptually, what we're going to get will be, in order for S to establish R, you can start from any of the values that satisfy the weakest precondition, which is here. This is the theoretically weakest precondition. You can think about this is the largest set in which any value there can guarantee as the implementation to establish R. That's theoretically the largest set you can have. So now, after that, what we need to do is, finally, let's say if this is the precondition you choose to have for your program, you want to make sure Q is really within this particular weakest precondition. If you can prove that it is within this particular weakest precondition, that's correct. If it goes like this, if somehow the precondition you have is outside the WP, that's not correct. Guys, pause a little bit on this particular diagram and tell me if you're comfortable with it. Of course, so far we haven't talked about how you calculate WP. That's going to be the rest of the lecture. But now I want you to make sure you understand the big picture over here. You're always given some implementation, S. You're always given some post condition from which, you're going to follow some systematic procedure to say, given S, given postcondition R, I'm going to calculate what's the theoretically the weakest precondition for me to start. However, the actual precondition you choose does not have to be exactly the weakest precondition. It can be anything that's stronger, anything, or equivalence. So that's why all you got to do is to make sure, eventually, you want to prove that the actual precondition is no weaker or stronger than the WP we calculate. That's the idea. If you can find any counterexample that is going to satisfy, let's say, the precondition by another WP, in that case, you got some trouble. Okay, we'll see the example like that. Any questions? Are we all right? Guys, are you sure? Wow. This part is very important for the exam. That's why I want to go slowly with you. Okay? You want to make sure you really follow that. Okay, good. We got about 5 or 7 minutes. Let's do a little bit more. Okay? Okay, so now WP is called the weakest precondition for the implementation S to establish R, assuming termination. So now what can the implementation be? It can be assignments. We're going to talk about it. Assignment is very easy to prove termination. It always terminates. Okay? It can be alternation, or like if statements. It can also be sequential composition. In Java, you simply got semicolon. In iPhone, simply like a new line, right? Line by line. And also we got loops. So loops is something that's going to be challenging. So we might only be able to get to loops when we talk about the makeup lecture on Friday. But I'll make sure I do that properly, so you can do the question on the exam. So now we're going to learn about how you can calculate the WP for each of the programming constructs. And let me draw a little bit link to what you had for lab number 5. Yeah, lab number 5. In lab number 5, remember you simply got some recursive structure, right, for the composite, right? You got addition, you got implication, etc. Here, the definition for WP, you can think about actually, it's a very interesting insight I just realized. You can think about WP is like a visitor for your predicates. Let me write it down and think about it. So when we talk about WP, S and R, think about this will be the program structure, which can be if statements, assignments, loops, etc. It's recursive. You can think about this is like a composite. And when we try to do the WP over here, this is more like a visitor. You're basically trying to visit the predicate structure and the implementation program and figure out exactly what a predicate should be for the weakest precondition. Okay? Actually, this can be a nice lab for the fall. Hopefully, you wouldn't have to do it, I hope. Yeah? Okay, any questions until now? Okay, so now let's basically, I'm just trying to give you some example over here. Okay, let's go over an example, and then we'll go to calculate WP. So now let's see this. Let's say you're given, let's say n is assigned to n plus 9, and then the postcondition n larger than 13, right? And some precondition, I'll just put question mark as a placeholder. It turns out, we'll see exactly how you can calculate this. N larger than 4 is really the weakest precondition, it turns out, after the calculation. So given n larger than 13, the postcondition, and given the implementation here n is assigned to n plus 9, we can calculate the weakest precondition should be n larger than 4. So now, depending on what question mark here is for the actual precondition, your program may or may not be correct, may or may not, right? Okay, anything that's equal to or stronger than would be okay. For example, n larger than 4, or it can be n larger than 5, right? It's stronger, so we are fine. On the other hand, anything that's weaker than that is not good, because you can always find counterexample. In that case, if you see n larger than 3, it's weaker than the weakest precondition. That's not good, because that's already the weakest. You should not go weaker than that. Okay? Okay, you can also do counterexample. This slide here just summarizes what we did for the two motivating examples. Okay, are we, and then I will get to this part here. Okay, just say one more thing. Remember the way we do the postcondition in IFO, you can use the O keyword to say that's a value in the pre-states, right? Now in mathematics, rather than using old, we're going to use the following convention. I'll just mention it to you. We're going to use that when we do the proof in the class. Let's say if you want to say old x, you can simply say x with a subscript 0, x0. Okay, that's a pre-state value. Okay, if you simply say x is a post-state value, x versus x0. Okay, so now just mention that quickly. So now if you say x0, that's a pre-state value. If you say x, that's a post-state value. Okay, and then we'll talk about it. Okay, let me just skip this part. You can read it by yourself. Let's just do the very first rule for the weakest precondition. Also, want to show you a little bit how you can read the precondition rule. So now, that's the first rule. Let's try to understand the structure over here. It's saying the following. I want to do a WP calculation. The first input arguments for WP is always a program. The simplest form can just be a single assignment. We got a variable x, which is assigned to the value that's denoted by some expression e. Okay? Upon the termination of this particular assignment, we want to establish a predicate called R. Okay? That's the most general form. Now, what should be the weakest precondition for that? So now let me just do one example here before I show you the answer over there. For example, you might have WP, and then x is assigned to x plus 9. X larger than 13. Okay, that's one instance of the problem. Okay, you can see that over here, x is assigned to e. You can think about this is like the x. And this guy over here is like the e. Right? And this guy here is like the r. Okay, you got x, you got e, you got r. You just got some pattern matching over here. So now, what should be the corresponding weakest precondition? Okay, you want to take a guess for anyone? Oh, you're taking 3342, so I don't think you want to answer. You want to take a guess? Anyone? That's okay, I'll just show it to you. This is going to be basically the same postcondition R, except every occurrence of x is going to be substituted by e. Intuitively, because we are trying to assign x to the new value e. So that means it's as if we are trying to say replace every occurrence of x in the pre-states by the new value is going to exist later by e. How do we understand that over here? Okay, let's apply the rule. So it's going to be x larger than 13. Okay, and now we're going to say the following. The variable we're trying to assign is x. We replace every occurrence of x by this particular e, x plus 9. Okay, how do we do that? Well, there's only one occurrence of x, which is going to be x plus 9. Okay, so now what we get is x plus 9 larger than 13. If you simplify that, x larger than 4. So this is the weakest precondition. I will explain the intuition to this, maybe start in the beginning of Wednesday. However, what I really want you to get used to before Wednesday, we're going to do another 3 or 4 rules about WP calculation. You really want to get used to exactly how to calculate this. Having the predicate over here, replace every occurrence of that by the value you're trying to substitute. Okay? And then you will get some simplification like this. Okay, I will stop here and then I'll continue from Wednesday.